The evolutionary transition from fin to limb occurred approximately 375 million years ago and is defined as the loss of fin rays and the origin of digits. Before the use of molecular techniques to study the fin to limb transition, conclusions were drawn by analysing fossils of transitional species. Sarcopterygian, the lobe-fin fish, are the sister group of Actinopterygian. The clade consists of lungfish, coelacanths, and tetrapods. The skeleton differs from Actinopterygian by having stronger skeletal elements which support a fleshier fin. Tetrapodomorphs is a group made up of all fossil Sarcopterygians that are more closely related to tetrapods than other extant Sarcopterygians. It is a member of this group that took the first steps onto land in the late mid-Devonian circa 380 to 375 million years ago. The typical naphostome paired fin is organised into three regions, from anterior to posterior: the propterygium, mesoopterygium, and metapterygium. In tetrapods, the metapterygium is divided into the stylopod, the zeugopod, and the autopod, along the posterior distal axis. Phylogenetically, the stylopod is the oldest of the structures, with the zeugopod and autopod appearing in more derived taxa. This order of appearance in the phylogenetic tree is recapitulated in the development of the limb. Tiktaalik, a crown taxa before the origin of digits, is known as the transitional species between fish and tetrapods. Tiktaalik has eyes and nostrils positioned on the top of the head, indicating a surface or shallow water lifestyle, and its fins with its fleshy palms were probably used to push the organism's head above the water surface to enable air breathing and capturing prey, or to escape predators by allowing them to navigate through dense mangrove swamps, rather than terrestrial locomotion. Evidence from the fossil record has shown fin ray asymmetry, which may be an adaptation to the loading from the ventral surface to prevent buckling from high ventral directional load. Unlike Euphenopteron and Tiktaalik, Acanthostega is digited and dermal fin rays are completely absent. Acanthostega has up to 8 digits per appendage, indicating pentadacty is not the ancestral state and that the number of digits has since reduced in many extant tetrapods. Analysis of the forelimbs of Acanthostega implies that the species lacks sufficient support for weight bearing. By analysing changes in morphology, accumulations of features characteristic of modern tetrapods can be tracked. Between Euphenopteron and Pandaichthyes, the fossil record shows there is a loss of midline fins, a flattening of the humerus, and a gain of supportive functions of the forelimb. The origin of digits and the enlargement of the hind limb and pelvic girdle is observed in Acanthostega. Ichthyostega fossils display elongation of limb bones and modification to the shoulder girdle. We can also see that the structure of the ankles in Acanthostega, Ichthyostega, and Euphenopteron were inflexible and not sufficient for weight bearing.
A number of key similarities and differences in the spatiotemporal expression of gene regulatory networks governing skeletal morphogenesis appear to have been integral to the evolutionary transition from fins to limbs. The dorsoventral structure, called the apical ectodermal ridge, plays a crucial role in axial pattern formation and is formed and maintained throughout tetrapod limb bud growth, however is lost in teleosts shortly after the fin bud appears. This heterochromic shift is thought to have been a primary developmental cause for the evolution of the first limbs. Morphogenetic formation of the apical fold in teleost fin development is guided by fibrils called actinotrichia made of elastoidin proteins and actinodins. Studies suggest that the evolutionary loss of actinotrichia may have led to this loss of skeletal structures such as lepidotrichia and paved the way for the transition from fins to limbs. The apical ectodermal ridge in both fin and limb mesenchyme secretes pro-proliferative proteins, and the perduration of this signaling activity in tetrapods creates a self-sustaining feedback loop, resulting in the distal formation of digits. It is thought that the sonic hedgehog and fibroblast growth factor regulatory circuit has an ancient evolutionary origin that originally functioned as a patterning mechanism for ancestral pharyngeal structures. Many comparisons between genetic regulatory networks in fishes and tetrapods have shown a high degree of conservation throughout vertebrate evolution. Cis-regulatory elements crucial for spatiotemporal transcriptional control in tetrapod appendages were already highly complex in the common ancestor of fish, showing that regulatory domains did not emerge de novo but merely underwent subtle changes. The forelimbs of mice and pectoral fins of zebrafish are a good example, as they use similar gene networks during development, such as fibroblast growth factor in the AER, sonic hedgehog expression in the posterior mesenchyme, and both early and late phases of Hox expression. Changes in downstream activity of the shared signaling networks mediate expression patterns of HOX-A and HOX-D clusters in the development of both fin and limb buds, and the acquisition of these HOX regulatory mechanisms likely led to the development of autopod and the loss of fin rays, with conservation of these tetrapod expression patterns demonstrated by their close resemblance to HOX13 paralogs in zebrafish. BMP antagonists such as gremlin-1 that mediate gene expression during fish embryogenesis have been shown to respond to inputs that regulate their expression in mouse autopods, further demonstrating a deep conservation that may date back to the origin of paired appendages.